Welcome to Brain Vision.
Okay, so this question asks us to calculate the mass of water in a mixture of water and ice, all contained in a container of negligible mass. All right, now we are told that the water has a temperature, let me say T1 being the temperature of water, being 80 degrees Celsius, okay? And then let's say T2 being the temperature of ice being negative 40 degrees Celsius. All right. And then the final temperature, let's say T subscript F being the final temperature of the mixture is 20 degrees Celsius. All right. Now, the mass of ice is 0.2 kilograms. All right. 0.2 kilograms being the mass of ice. Now, the specific heat capacity, let me say CH.C for water, CH.C for water is equal to 4190 joules per kilogram per Kelvin. All right. And then the heat capacity for ice is equal to 2100 joules per kilogram per Kelvin. Joules per kilogram per Kelvin. All right. So let's put these informations down before we go to our equation. Okay. Now, in this mixture, water loses heat to ice. Okay. In this mixture, water loses heat to ice. Now we are told that no heat is lost to the environment. Okay. So whatever heat exchange is between water and then ice. So these are the only two components that are sharing or are transferring energies and receiving energies. All right. So I will say that the heat lost by water, is equal to the heat gain by ice. Okay, it's equal to the heat gain by ice. So then our equation will now be mc delta T for water. That's for water. Is equal to mc delta T for ice. And remember, as the ice receives this temperature, there is a point where the ice also transforms from a solid state to a liquid state. And for that reason, we'll talk about the latent heat of fusion, which talks about the change of state without changing temperature. All right. Now, with this information given, we don't know the mass of water, and that is what we are calculating. So the mass of water times the specific heat capacity 410 into bracket the change in temperature, let's say 80 minus 20. I just chose to bring 80 first before 20, even though 80 is the initial and 20 is the final, which is supposed to be final minus initial. And if I do it final minus initial, I should attach a negative sign. But since I'm doing it initial minus final, then I ignore the negative sign. It's all the same. All right. So this is equal to the mass of I, 0.2, multiplied by its heat capacity, 210 times the change in temperature, which is let's say 20 minus 40, okay, and plus the mass of ice times the latent heat of fusion of ice or water is given as 334 times 10 to the power 3. Good. Now, when we do this, our mass multiply by all of this, which will give us 251,400 is equal to the evaluation of this equation, which gives us 25200 plus 6,6,8,0. Okay, all right. So at the end of the day, we're gonna have m is equal to 25200 plus 6,6,8,0, all divided by what we have here, which is 251,400. Okay, so at the end of the day, you have m is equal to 0.37 kilogram, which is the mass of water in that mixture. All right, as at that temperature. Okay, all right. So basically, that is it for calculating the mass of water. All right.